It has almost been 2 weeks since the first recording. So far, the crystals have grown only very little. This might be due to the fact that the aluminum bottle was carried to the lounge when I was first filming my first video, causing movement of the solution that might have led to the interruption of the process of recrystallization, which requires minimal disturbance. Moreover, the light inside my room might have also been a source of disturbance as it carries energy that might also have interrupted the crystallization of alum. Lastly, it is possible that the humidity of the room may have affected the evaporation process as the equilibrium of evaporation of the solution will tend less towards the gaseous state than in drier conditions. This would decrease the probability that the solution is saturated and that the crystals would form. As for the yield of alum that should be theoretically reached through this experiment, we could refer to the stoichiometry in order to calculate, from the initial amount of aluminum foil utilized, the amount of alum that should be produced if the reaction occurred in a perfect medium with no errors. The first reaction involves aluminum and potassium hydroxide. We first calculate the limiting region through the following process. First, calculate the number of moles of KOH through the use of the equation the concentration equals to the number of moles divided by volume. We were given the concentration of the solution and the volume, so all we have to do is calculate the moles of KOH. Next, to find the number of moles of aluminum, divide the mass by the molar mass, which was found to be 26.98 grams per mole. To find that, 0.037 moles of aluminum were produced. Next, divide the number of moles of each compound by its stoichiometric coefficient, which in this case is just 1. The compound with the smallest value corresponds to the limiting reagent. From the following calculations, we can see that aluminum is the limiting reagent, and the number of moles of aluminum reacting in the reaction corresponds to 0.037 moles. Next, we can use the ratio of aluminum to alum in order to find the number of moles of alum produced relative to the number of moles of aluminum reacted. From the equations, we can see that this corresponds to a ratio of 1:1, as there is 1 aluminum in alum. We then multiply the number of moles of alum by the molar mass of alum, which is equivalent to 474.39 grams per mole. The theoretical yield of alum that should be produced from a gram of aluminum through these reactions should be of 17.56 grams. The experimental yield measured in the experiment was of 18.68 grams. To calculate the experimental percent yield, we can use the following equation. Percent yield equals to experimental yield divided by theoretical yield times 100%, which is equivalent to 106%. The experimental yield was not exactly of 100%. It is in fact larger than the experimental yield. This is probably due to the many errors performed throughout the laboratory experiment. These errors can be categorized into random and systematic errors. Systematic errors will contribute to the decrease only or increase only of the output of a product from the reaction. Random errors are less predictable. However, the error that is most likely to have the biggest influence in this reaction is the involvement of the impurities and incomplete reactions, which lead to a weight that is higher than that of the theoretical yield. To explain further, the chemical effect of the impurities that failed to be removed from the sample might have reacted and influenced the chemical makeup of the sample. This error is random, and as there might be different possibilities that might lead to both an increase or a decrease of the experimental yield. Lastly, the fact that the reaction might not have went to completion might create a gap between the magnitude of the experimental and theoretical yields of the reaction. On a final note, another possible source of error is that the product might have been lost over time due to leftover solution in the glassware, where the solution was contained and transferred. This was magnified in this experiment as it was composed of several steps, which means much more product might have been lost over the course of the experiment.